Hi everyone. So this is Unit 4, Lesson 4, negative and zero exponents. This is going to be the last lesson in this section before your test. So learning goals here, you are going to have to rewrite negative exponents as positive exponents, evaluate expressions where a number is raised to the exponent 0, and solve problems related to exponents. So this is a sort of easier lesson at the end of the topic. It's going to be a little bit shorter. And I'm also going to show you why these things work. So we'll start with negative exponents. So I can just tell you how that works, and I will, but let's connect negative exponents to what you already learned in grade 9. So you would have learned the product law when you're multiplying powers that have the same base. So you've got a number here a and an a there. So both of these numbers are bases, right? The base is the number under the exponent, and this is the exponent. So both bases are the same. They're both a. So if you're multiplying two numbers that have the same base, you can just add their exponents. So a to the exponent 3 times a to the exponent 4 is equal to a to the exponent 3 plus 4, or a to the 7. Quotient law is very similar, except it says that when you're dividing, you just subtract the exponents. Again, the bases have to be the same. So a to the exponent 5 divided by a to the exponent 3 is equal to a to the 5 minus 3, or a squared. But to understand negative exponents, let's see if you can see what happens. What if we reverse the example in our quotient law? What if instead of a to the 5 divided by a to the 3, it was a to the 3 divided by a to the 5? Well, that would give us a negative number, right? Because if we subtract our exponents in this case, we get 3 minus 5, which is negative 2. So this kind of hints at what the negative exponents are going to turn into, because if you look on the left-hand side of this equation, we can simplify that. So let's see how that works. So a to the 3 divided by a to the 5, we can cancel, right? Remember that a to the 3 means you have a multiplied by itself 3 times. You have a times a times a. On the bottom, you have a times a times a times a times a, right? 5 times. So your 3 a's on top will cancel with 3 a's on the bottom. And so what you end up with is all of your a's on the top are gone, so you're just left with 1. Right? Because you can think of, if you have 3 a's on there, that's 1 times a times a times a. So everything's canceled except the 1. And the thing on the bottom, you've canceled 3 a's, so we have a squared. So 1 over a squared equals a to the negative 2. And so that's the general rule for negative exponents that's related to this is if you have some number raised to a negative exponent, that's just equal to 1 over that same base raised to the same exponent except positive. It's real easy, right? Any number to a negative exponent is just 1 over the same number to the same exponent, but positive. Okay, so it's a useful way of getting rid of negative exponents, and if you know this, then you can quickly compute what a negative exponent is, maybe even in your head. Okay, so quick example here. Rewrite each power using positive exponents, then evaluate. So if we have 5 to the negative 3, well, you just do 1 over that number, and 1 over 5, so you get 1 over 5 to the exponent positive 3, right? The negative changes to a positive, which is just 1 over 125. Simple. In this example, it's a little bit more complicated because now we have a fraction. So 2 over 3 to the negative 4. So in theory, you could write this as 1 over 2 over 3 to the positive 4. But if you think about it, when you're dividing fractions, right, if I do 1 divided by 2/3, remember your rule for dividing fractions? 1 divided by 2/3 is equal to 1 multiplied by 3 over 2. You have to flip the fraction and multiply. So we can just do that quickly. So instead of writing 1 over 2 over 3, we can just flip it and make it 3 over 2. So this is the same as saying 1 over 2 over 3 to the exponent 4, but we just write it as 3 over 2 to the exponent 4. Simple rule here, if you have a fraction, just flip it and make your exponent positive. Okay, so remember when you have fractions with exponents that you have to apply the exponent to the top and the bottom. So when you do that, you get 81 over 16. Okay, what about zero exponents? So again, if we look at the quotient law, we can understand where this rule comes from, and this will be the rule down here. So let's just say you have a to some exponent minus itself, because that's a to the 0, right? So I do a to the 3 minus 3. I could have made this 2 minus 2 or 6 minus 6. It doesn't really matter. But the point is that I have what's equal to a to the 0 on the left side here. And again, let's translate that into the same sort of form we did here. If I have a to the 3 minus 3, what does that mean? Well, that's just a to the 3 divided by a to the 3, right? Remember, by our quotient law, I can take this and write it that way, right? Both of these things have the same base. I'm dividing them, so we're subtracting the exponents. So these two are equal. So a to the 0 is equal to a to the 3 divided by a to the 3. And that, of course, everything just cancels and gives you 1. So a to the exponent 0 is equal to 1. And that's our rule. So for any x, if you have x to the exponent 0, that will be equal to 1. There is one exception to that, which we'll quickly explain. Okay, so the exception is that x cannot be 0. So 0 to the exponent 0, you can try that on your calculator. That's not going to give you 1, it's going to give you an error. So why will that happen? Again, if we use the same setup, once we get a to the 3 divided by a to the 3, you'll notice that if a is 0, then that gives you a 0 in your denominator. And you can't divide by 0. So anything to the exponent 0 is 1, except for 0. If you raise 0 to the exponent 0, you have basically undefined, right? You have no answer. Okay, so very quickly here, these examples, it doesn't matter if you're dealing with a number like 5 or a fraction, any number raised to the 0 is 1, except for 0 to the 0, which is undefined. So that's a really fast example. All right, on to our last problem here. So we're going to look at a word problem. So if you look in your textbook in this section, they talk a little bit about radiometric dating. So here we have carbon-14. If you've ever heard of carbon dating, that's what this is talking about. So carbon-14 is a radioactive element that decays to 1/2 or 2 to the negative 1. Right? Think about that for a second. 2 to the negative 1. If I want to make that positive, that's going to be 1 over 2 to the exponent 1, which is 1/2. So 2 to the negative 1, or 1/2 of its original amount after every 5,700 years. So we want to determine the remaining mass of 10 grams of carbon-14 after that length of time. So I'm only going to do part A. I'm going to leave part B for you, although the answer is on this sheet, but I haven't showed you how to get it. But the way you get it is pretty much the same as A. So let's add a little bit of terminology here to help explain this problem. So you'll see probably this elsewhere. If you take advanced functions later on, they have these sorts of problems, but they're a little bit more complicated. But carbon-14 is an isotope. So if you've taken science, right, you might know about protons, neutrons, and electrons. So carbon-14 is a variant of carbon that has 8 neutrons, right? Carbon has 6 protons, and this one has 8 neutrons. But anyways, it decays after 5,700 years. So basically that means that some of the protons or neutrons are lost. There's a whole bunch of different reactions that can happen. Actually, there might be electrons in this case. I've forgotten. But whatever. What happens is that you no longer have carbon-14. It changes into something else. So after 5,700 years, some of the carbon-14 has changed into something different, and it no longer exists. So in fact, after 5,700 years, half of your sample has changed into something else. So we say that 5,700 years is a half-life. Okay, so every 5,700 years, half of what you have disappears. So if you have 10 grams of carbon, in 5,700 years, you're only going to have 5. You lose half of it. Okay, so with that in mind, how much carbon-14 are you going to have left after 11,400 years? Well, if half of it disappears in 5,700 years, let's figure out how many so-called half-lives we have. So basically what we want to do is take this number, the number of years in the problem, and divide it by 5,700. Let's see how many half-lives fit into that. And the answer works out nicely to 2. So what this means is that you're going to go 5,700 years and lose half of your sample. Then you're going to go another 5,700 years and lose half of that. And if you add those two together, that's 11,400 years. So how do we understand this in terms of exponents and all that stuff that we're doing? Well, this can be a formula that you can use for half-life. So the amount that you have at any given time is equal to the initial amount that you started with times half raised to the exponent, which is the number of half-lives. Because every time you have a half-life, you lose half. So you lose half, right? Remember, of means multiply. So half of half of half, you're multiplying all those halves together. So half of half of half is half to the exponent 3. That's why we use exponents here. So this is an exponential relationship. You'll learn more about those later in grade 11, but for now, just as long as you can understand how this works, that should get you through all the problems that you have to cover. Okay, so you can just use this formula here. By the way, when we say exponential, it's not linear, it's not quadratic, it is something different. So, what we said is you have 10 grams of carbon to start with, so that's your initial here, and you're going through 2 half-lives. So you calculate how many half-lives by dividing the number of years by how long the half-life is. So we have 2 of them in total. So what that means is that we can now plug in our numbers. So we have 10 here, and then the exponent 2 there, and we get our answer. But again, just to try to understand it, what we're saying is we have 2 half-lives because we have 5,700 years plus another 5,700 years. So another way to understand this is what we're saying is start with 10. Then after 5,700 years, you have half of that. So you have 10 times half, which is 5. Then after another 5,700 years, you have half of that. You have half of 5, which is 2.5. So that's all this is really saying here. Okay, so it's a problem, so we need our therefore statement. And I'm going to let you do part B. So the answer for part B is approximately 0.31 grams after 28,500 years, but the way that you do the problem is the same, right? So you can figure out based on this and based on this how many half-lives you have, and then just use the formula. Okay, that's all there is to this lesson. So basically what you should remember, can you write negative exponents as positive exponents? Simple rule, x to the negative a equals 1 over x to the a. Can you write evaluate expressions where a number is raised to the exponent 0? Well, any number to the exponent 0 is 1 except for 0 to the exponent 0, which is undefined. And then can you solve some problems like our half-life problem that we just covered? By the way, if you're interested, this is not something you have to know, but this stuff's kind of interesting. So if you want to learn more about carbon dating, you can just read this little thing here. Kind of cool. All right, take care.